and welcome to ELF University's Electrical Engineering and Computer Science Course 302, FPGA Design for Embedded Systems. It's Day 4, an introduction to Verilog. I'm your professor, Qwerty Petabyte, and I've been looking forward to this class for some time now. Let's start off by reviewing some of the information that we've already covered. An FPGA is a field programmable gate array. It's an integrated circuit or chip that can be used to design custom task-specific digital logic. An FPGA is almost magical in that it allows you to create and edit actual digital logic circuitry. Its close cousin, the ASIC, is an application-specific integrated circuit. Generally speaking, once a design is created, tested, and proven to work on an FPGA, that design can then be used to create an application-specific IC. ASICs are cheaper and faster for production at scale. Custom task-specific digital logic can be orders of magnitude faster or more power efficient when compared with software running on a more general-purpose CPU. Let's review some of the other information that we've covered over the last 3 days. We covered the history of the FPGA when they were originally developed as North Pole technology back in the 1950s. They leaked to the human world then in the mid-1980s, and they're still in use today. FPGAs and ASICs, well, we're not using them as much here up at the North Pole because we have sentient AI based on quantum computing and nanotechnology that have replaced most of our elves working on design. Why should we learn this technology then? Well, FPGA development is a wonderful introduction to parallel processing concepts. The technologies that we're going to be using in our class, we've discussed a little bit. We're going to be beginning with old school Verilog 2005. And as the class progresses, we'll introduce System Verilog. Remember, as I always say, you need to learn to walk before you learn to run. Let's do a quick introduction to Verilog. It's important to understand and compare and contrast the difference between developing integrated digital logic circuits, which was what we're going to be doing in Verilog. We want to contrast that with developing software in a programming language. This class assumes that you have some sort of a background in programming, but I'm telling you right now, you need to forget all of that. We're not, I repeat emphatically not, programming a computer. You need to get that idea out of your head. We're doing something very, very different. We're going to be designing hardware in what is called a hardware description language, HDL. And the type of hardware description language we're using is called Verilog. Do not approach writing in an HDL with the same mindset you use when programming. An HDL describes the function and interconnection of digital logic components. It's not an interpreted or executed language like Pascal or Python or C. You must unlearn what you've learned because we're not writing programs. Let's talk about the difference between those two concepts. If we were writing code in C for an Arduino to blink an LED, we would use a loop that included delays. In this case, you can see here, this is the code for the blink SketchUp for an Arduino. We have some setup that runs and as the power comes onto the board and initializes things, but then it jumps into this loop where we do a digital write to turn the LED high or turn it on. We then delay for 1,000 milliseconds. Then we write again to turn the LED off, and we delay for another 1,000 milliseconds and then begin looping around again and again. This is how you would write code in C to blink a light, but we're not writing programs. Here is the same concept developed in Verilog. Notice we're not writing loops. We're creating actions that take place based on specific events. In this case, rising clock edges. The clock on our system here runs at 100 megahertz, and we are trapping on every positive clock edge of either the clock or the reset bus, and we're doing things when that happens. So, for example, when our board is reset, we're going to be doing these things. We're going to set our counter to 0 and set our blinker value to 0 as well. That's the equivalent of the initialization in our C program for the Arduino. Every time our 100 megahertz clock line goes high, we're going to perform other actions. So, for example, every time the clock goes high, we increment our 1 second counter. When our 1 second counter reaches 100 million, we know a second has gone by because our clock runs at 100 megahertz. When that happens, we do some very specific things as well. We set our counter back to 0 so we can begin counting the next second, and then we set the blinker value, if it's a 1, to be a 0, or if it's a 0, we set it to be a 1. This blinker register's value is tied to our blinky output, which is then in turn tied to an LED on the board. This is very, very different from the loop-based concept that we saw in our C program to blink the lights on the Arduino. Let's talk about some of the HDL concepts that are evident in our blink module. This was written for Digilent's Basis 3 board, and it highlights some very important points about writing HDL or Verilog code. Modules have inputs and outputs. These inputs and outputs are connected to real-world things. In this case, the 100 megahertz clock on our board and the reset line make up our inputs, while our output, which we call Blinky, is connected up to an LED. We don't really have variables either. Data is actually stored in registers, which are physical digital logic components that exist on our board. We perform actions based on events, clock edges, board resets, power cycles. Even something as simple as monitoring a button push is performed in the context of a clock edge. Button pushes also have to be debounced using smaller separate Verilog modules, and we'll cover that in a later class. But the thing to recall and the thing to understand is that all of this activity occurs in parallel, which makes FPGAs and digital logic design incredibly powerful. As if to push forth this idea that we're not programming and writing software, here is our blink code implemented as interconnected logic gates within our FPGA. This is the actual outcome of what you would consider to be the compiling step of our Verilog code. It creates these interconnected logic circuits within our FPGA. To the left-hand side, you can see two inputs, our clock input and our reset line input. To the far right, we see Blinky, which is our output that will go to the LED. Let's take a look at today's assignment. As you know, our semester project is creating a sound chip for the new Curse 'em Out Karen doll. Before we can make her say that trademark phrase that has made her famous, "Let me talk to your manager," we first need to get her making noise. Remember, we have to walk before we run. We're going to start by using Verilog to create a simple square wave generation module. The idea will be to divide the 125 megahertz clock frequency of the FPGA we're using for this design to provide whatever frequency we'll need to create Karen's voice. In our blink module, we divided the Basis 3's 100 megahertz clock frequency down to create a 2 hertz square wave to blink the LED. Now, in our assignment, the required frequency will be specified as a 32-bit input register called Freak. The value is going to be passed in as 6 digits, specifying a frequency of 4 digits of actual numerics and 2 decimal digits. For example, if we passed in the value 2, 3, 4, 5, 6, 7, we'll be specifying a 2,345.67 hertz square wave. You should then output that square wave, alternating between 1 and 0 at the desired frequency, to the wave out output. Remember, a square wave should have a half-duty cycle, meaning that it's high, or 1, for half the cycle, and low, or 0, for the other half. Our LED in the blink module was on for 1 second, then it was off for 1 second. It was being driven by a 2 hertz square wave, not a 1 hertz square wave. This is critically important because if you don't take this into account, you'll be creating the wrong frequency. To create a 1 hertz square wave in blink, we would count to 50 million, not to 100 million. To be as accurate as possible when creating your square wave at a particular frequency, you're going to be required to do some mathematical rounding. Mathematical rounding is when, if something has a 0.5 or greater, we round up. If the decimal is below 0.5, we round down. You're all smart students who have a lot of programming experience under your belt, so I'm sure you'll figure it all out. But just in case, I may have slipped a little hint into my introduction on the homework website. Thank you for attending today's EECS 302 lecture. Tomorrow's lecture, day 5, will be on pulse width modulation as we move forward in making Kirsten Karen say her trademark phrase. Have a wonderful day, and remember, Verilog is very user-friendly. It's just very choosy about its friends.